Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials in Manufacturing Innovation, IMMI. Here's a new paper in our journal, MicroProcSim, a software for simulation of microstructure evolution. This paper comes from corresponding author Pınar Acar and her Astro Lab at Virginia Tech, along with contributions from Northwestern and University of Michigan. So let's get into it. MicroProcSim is a tool for simulating microstructure. The authors start out by pointing out that this is actually a long-studied thing. We obviously care a lot about how microstructure evolves under mechanical deformation because it leads to new properties and new performance. And there's been a lot of work done here. They talk about the foundational models, like the original Taylor model and its variants, the sort of intermediate complexity approaches, Lamel, advanced grain interaction, RGC schemes, all the way up to the more sophisticated ones like viscoplastic self-consistent or the elastic rigid plastic self-consistent models, all the way up to the sort of state of the art, which would be crystal plasticity finite element models. Now it's awesome. They point out that there's this range of different tools available, but the best ones still come at a high computational cost. So what the authors have built here with MicroProcSim is a tool they're aiming to be competitive with some of these high fidelity simulations at a much lower computational cost. How are they going to do that? Well, they're going to take advantage of the orientation distribution function. If you're not familiar with that, the orientation distribution function is essentially a way of calculating the fraction of different orientations occupied in your crystal structure. For example, if you were to consider that your crystal structure has these, representations of the different orientations available, we want to capture the distribution of these different orientations, and we do that in these ODFs. Why do they like that? Well, for one thing, they like it because it's a convenient method to representing the structure. It's a one-point probability descriptor that sort of simplifies complex analyses. In other words, we're not going to track every single grain. We're going to use this overall representation of the structure and use that to model how materials change under different mechanical loads. They point out that it has simplicity of localized nature of these polynomial functions, lets them effectively model sharp textures. It points out that the finite element framework facilitates the construction of texture transformation analogs, just like interpolation, differencing, and projections. And finally, that the Rodriguez parameters uniquely map each orientation to a specific position in the Rodriguez fundamental region, so you end up with an unambiguous representation. Here's the thesis of what they're trying to achieve. It says we've developed our software package they're calling MicroProcSim, which can capture the texture evolution of cubic microstructures, under different loading conditions. It's capable of simulating a wide range of materials processing conditions under various deformation modes that alter the microstructural texture. Additionally, the strain rate and initial microstructural texture can be customized then to replicate real experimental conditions. When you get into the actual methodology, there are a couple key assumptions and sort of approaches that they rely on. First is the ODF, obviously, that they're using, and the Rodriguez vectors. Another is that they're assuming Taylor's hypothesis, which is essentially saying that there's a uniform velocity gradient across all your grains. They also use lattice spin as the reorientation velocity driver under applied deformation. And the approach is able to model a variety of different mechanical loading from, say, tension, shear, and even rolling. Here's what the software architecture ultimately looks like. The inputs then are going to be the initial random texture and the external load, along with the slip parameters and the strain rate. These are taken into the actual simulation, which does a plastic deformation modeling of these cubic microstructures, and the output is then the actual texture evolution over time. So what does it actually look like? Here's some samples of the microstructures in the Rodriguez orientation space, and what you're seeing here, this was normal strain in the X, Y, and Z axes and what the resulting texture would look like. Similarly, it can be done for shear. So here's shear in the XY, XZ, and YZ planes. And then strain compression from rolling, similarly done in 3 different directions. What you probably care the most about is how well does this actually agree with experiment. So here's an example. Here's a tension experiment, and in the top you're seeing what the experimental pole figures look like, showing you the evolution of texture in the different orientations. And then here's the sort of expensive, this is Prism's plasticity TM modeling software in the middle, and in the bottom is their MicroProcSim microstructure, and you can see that it agrees pretty well. Similarly for shear, you can get good agreement. And for rolling, it can capture the sort of complex microstructures that evolve from rolling as well. So this is slick software. In fact, it's been around a while. There's several publications they point out in here that are already using this. But here in this paper, they're outlining how it works and how it's been deployed. And I appreciate that they're actually even talking about how it's been developed for both Windows and now for Linux as well, and what those sort of pathways look like and the software tools they use to make it happen. So check it out in the latest issue of IMMI.